Now we can use the exact same method as we used with equations to solve complex inequations by using graphs. We're going to graph the y equals the left-hand side and y equals the right-hand side on one sketch, and then have a look this time at which values of x are not the solutions of where it's equal, but where they cause one curve to lie above the other. So similar to solving an equation, you want to find where the crossover points are, the intersections, but then you need to interpret what that means. So using this example, a bit of revision, graphing something like this. Some of you may have had trouble graphing something like this in year 11. There's a couple of ways you can do it. One way is to say, well, I know that the basic form of an absolute value graph is it's got this V shape, okay? But this one is not x, it's 2x, so that tells me that it's going to be a steeper one. So it won't look like that, it will be like y equals 2x, except it can never go, y can never be negative, because this side can never be negative. It's got an absolute value on it. So that means it bounces up like this, and it's a bit sharper, because it's got a gradient of 2. Then you can say, all right, but hold on, we've shifted it to the right. Now notice we haven't shifted it to the right 5 units. If this said x minus 5, then sure, we'd have shifted it to the right 5. We've actually only shifted it 2.5. And the reason we can see that is because we've got 2x minus 5 here, and if we solve 2x minus 5 equal to 0, what we get is that x is 2.5. And that will be our x-intercept. Okay, when y equals 0, sorry, all I've done here is I've let y equal 0, and I've found that I have an x-intercept right there, and that's at 2.5. So I've actually only moved the curve across. So I've drawn it here, it's got this characteristic V shape. If you get confused with absolute values, the other thing that you could have done to graph this thing is to literally draw up a table of values and say, all right, we'll just start with some negative ones and just have a look at what this graph does. It's always a good backup. And you could have plotted some points here. Remember that it's got that characteristic V shape and plotted it in. Okay, so we've plotted our absolute value graph. Now we need to plot this one, y equals x plus 2. You should recognise that that's just a straight line with a gradient of 1 and a y-intercept of 2. So I've drawn that in here. It's going through 2 on the y-axis, and it's going up with a gradient of 1. Now, when it comes to finding your solutions here, you'll need to still work algebraically, but at least we're not having to deal with the awkwardness of the absolute value part. Don't forget that this straight line here, if we could draw it going all the way through, would be y equals 2x minus 5. And this part of it over here is y equals minus 2x minus 5. Now notice I put the minus and then I put the brackets. What you need to think through here is that 2x minus 5 could be positive or it could be negative. So looking at the two parts of it, and we take those two lines and basically put them together but only use the positive values of them, which is what rubs out this part. It's much easier if you know what you're dealing with. Now, this line here, you might write it down like that, then expand your brackets out and say that's minus 2x plus 5, noting that you've got a negative and a negative here. So we know what this line is. So solving our two little equations algebraically there to find what our 2 points are, let's just let them equal each other. So on this one, we've got the line 2x minus 5 equals x plus 2. We can easily solve that. Take x off each side, add 5 to each side, and we know that happens when x equals 7. Have a look at your graph and think, oh yeah, that looks like about 7, that seems about right. Now we can solve to find this one. We can see it looks like it's around about x equals 1. If you had to guess, you'd probably guess that anyway. But just to check it, we can say, all right, this is minus 2x plus 5, and we want to let that equal x plus 2. So I've basically just taken the negative version of this. But notice how I took care of the signs here, and I didn't make a classic sign error with the negative out the front of this whole thing and the negative in the middle, gave me a plus there. Now if I solve this, then I can add 2x to both sides, that gives me 3x here, subtract 2 from both sides, and sure enough, x is equal to 1. Now, have a careful think now, we're not trying to find the solution of this to say that x equals 1 or 7. We're trying to find the parts or the values of x where our absolute value function is greater than or equal to our straight line. So we've got our key points now. We've got x equals 7 and we've got x equals 1. They're our points of interest. And we can see now that this V shape is going to sit above the straight line up here, that's where it's above it, and over here. So they're the two sections that we want, and that would be for the values of x that are 1 or smaller, or 7 or bigger. So we get two solutions. We can list them. X must be less than or equal to 1, or x must be greater than or equal to 7. Now referring back to an example that we already looked at with equations, we solved this one earlier and we said let's draw y equals 2 to the power of x. Let's draw y equals x plus 2, and where they cross over, those will be the solutions for x. And we found this one was exactly 2. And this one, we knew that this point here is minus 2, so we approximated that this was probably around about minus 1.7. We didn't have it exact, it was an approximation. Okay, so how does that change if we put one of these less than signs in there? Well, what we're saying is, tell me the values of x where this curve, y equals 2 to the power of x, is sitting below, actually sitting lower down than this straight line. Well, let's use our red pen here and see where is the curve lower. Up here it's higher, and up here and along here it's higher. The part where it's actually below is this section here, isn't it? Because here our curve is below our straight line. So those are the values of x that would solve this equation. Now one of them we can lock in because we found it exactly. X is less than 2, and it would have to be greater than our minus 1.7. This one was an approximation, but that's okay. We've got a bit of an idea of the range of values that would satisfy this inequation.